In this video, we're going to discuss how we can build several common models that are used in order to fit a regression model that accounts for the clustered nature of the data. So, we've been talking about a lot of details regarding the interpretation of a hierarchical linear model. But here's the good news. Depending on the situation, we may not have to have all of those components in the model at the same time. Very often, we're just looking to account for the nesting that's involved with the level two variables when we're analyzing things within level one. So that is to say, I really am just trying to study how an employee's skill level relates to their salary. And I know that companies involved here, but that's not something I'm really trying to focus on. I just need to account for the company level variable, that nesting, when I'm analyzing these level one variables. Within this context, there are three common model types that we can use for this purpose. The first one is called an intercepts only or a variance components model. This is analogous to random effects ANOVA in that we don't have an independent variable. All that we have is a fixed intercept, that is our default value for everybody, and then we allow this intercept to randomly change based on the level 2 groups. We can use this intercepts only model to test if level 2 is really contributing anything to the analysis. And ultimately, this ends up being a great default test of if HLM is appropriate in the first place, or if we should just run a regular regression model without accounting for the level 2 clustering. This statistic that we can calculate is called the interclass correlation coefficient. The second common model is called a random intercepts model. And I want you to think of this as a regression model where we're allowing the intercepts to be different for each value within level 2. So in our case, we just look at a regular old regression model, looking at how skill is related to an employee's salary, but we're going to let all of the companies have different base salaries in order to account for the fact that different companies might be different from one another. I find this to be a really, really good model. It's not always the best fitting model, but it's a good balance between ignoring clustering completely and dealing with a whole ton of complex interpretations. With a random intercepts model, it allows me to account for clustering at least at the intercept level. That is, every company can have a different base pay, and I can still get my regular regression coefficient interpretations without making them too complex. So it's a nice balance between the two. For situations where I think that skill compensation might vary by company, I could use the random slopes and intercepts model. So this is similarly a regular regression, which allows the intercepts to change, but it also allows the slopes to vary by company. And ultimately, the decision between the random intercepts and random slopes model should be made based upon theory. That is, I believe that different companies allow different base pays, but have a consistent salary structure for skill increases. Or I think that companies uh, have different base pays and have different salary structures for skill increases. So let's start building some models. We're going to go through and build them out. Again, we're going to use the same context with level one as the employee and level two as the company, looking at employee skill related to employee salary. And the level two variable that we're going to look at is private versus public. This is going to be W. So we'll be using a data set. The x-axis, that is the horizontal one, is representing the employee skill level, and the y-axis, that's the vertical one, is representing the employee salary. And we can see generally as x increases, that is, as you moved from left to right, the y increases. It goes from bottom to top, indicating that more experienced individuals tend to have higher salaries, which we would expect. So let's talk about the intercepts only model, this first one. This is a very common model to fit at the very beginning of an analysis, and no matter what eventual hierarchical linear model you end up using, you will tend to start by fitting an intercepts only model, and we'll talk about why in a second. So this model on the screen is our full model, but again, we're not going to use all of the variables for an intercepts only model. In fact, we're not going to use most of them. So let's see what we're actually going to end up using. For the intercepts only model, we're really just going to use the beta 0j components, and not even all of those, and our epsilon sub ij. Putting these together, I'm going to end up with gamma sub 0, 0, which is my fixed intercept. That is the number that is kind of the average for everybody. The U sub 0j, which is the random company effect, each company having a different base pay, and epsilon sub ij. This model is very useful for testing if level 2 is really contributing anything at all in the first place. Ultimately, what we end up testing is the variance or the movement of U sub 0j. And if you think about it, U sub 0j represents a company's difference. So different companies have different base pays. And if there's not a lot of movement, that is, U sub 0j doesn't require a bunch of adjustment, that would indicate that companies may not have particularly different base pays. On the other hand, if there's a lot of variability, if U sub 0j is jumping around a lot, that would indicate that each company requires major adjustments to reflect that company's base pay, and so we would have a large variability there. The statistic that we can calculate related to this is called the ICC, or the interclass correlation coefficient, which we'll discuss in more detail in a second. Ultimately, in a similar way to the coefficient of determination that we discussed in the review part, this represents the percent of variance in the salary that the level 2 model, in our case company, explains. If this is high, a high percentage of variance in the outcome, salary, is explained by the level 2 variable company, then we would say that including the level 2 set of models is important, or hierarchical linear modeling is the appropriate modeling approach for that data. Gamma sub 0, 0 is the intercept, as we've talked about before, the grand mean or average salary overall, with U sub 0j representing the random intercept or the adjustment to the base salary for company J. As always, epsilon sub ij represents the error or unexplained variability in salary at the individual level. So let's see what this actually looks like if we do it. We have our base data, and if we implement the intercepts only model, what we end up with is something that looks kind of like this. The dotted line represents gamma sub 0, 0, the overall average for everybody. And each of the colors represent the individual company adjustments that are made to that. So each company is allowed to have its own base salary. You'll note that all of these are horizontal in that they're just a single number guess, an intercept only model. We have a single number for each company that's represented by those colorful lines. The test of variability for U sub 0j asks, is there variance in the different colors? Or are all these colors very closely clustered around the black dotted line? Or do they move sufficiently for it to be worthwhile to account for the differences between company and base salary? Again, this ICC, interclass correlation coefficient, is very strongly related to R squared in the sense that it's, in a way, the percent in the variance of the outcome explained by level 2 of the model. We can calculate it simply by taking the variability of U sub 0j and dividing by the variability of U sub 0j plus the variability of epsilon sub ij. And these variance components are things that are output by our statistical programs. So these are going to be pretty easy to find, and we just plug them into this equation. Sometimes you'll see this listed as tau sub 0, 0 divided by tau sub 0, 0 plus sigma and rho on the left-hand side. In this form, rho on the left-hand side simply represents the interclass correlation coefficient. Tau sub 0, 0, as the placement suggests, simply represents the variance of U sub 0j, and sigma simply represents the variance of epsilon sub ij. All right, let's discuss the random intercepts model. So in the random intercepts model, we'll be simply using these components. So we keep the same components from beta 0 sub j, beta sub 0 j, but now we're adding a fixed component in beta sub 1 j. That is, we're adding a single value gamma sub 1 0, which ultimately is going to be interpreted as our old beta sub 1. Looking at this model, I want you to consider that if we just erased out u sub 0 j in the combined model, this is our regular regression, a regular simple linear regression. Let me say that one more time. If you just erased out u sub 0 j in the combined model, I would have a regular linear regression, simple linear regression, a single independent variable and a single dependent variable. I say this to help you understand that this is a very, very, very familiar model, and interpretations are hopefully going to be familiar too. Ultimately, this model is used to test the relationship between X and Y, or in our case, skill and salary, after accounting for the differences in the company base pay, or that U sub 0j. Again, I think this is one of the best models because it balances that feature of being our regular regression model, just with that U sub 0j, with accounting for the differences in company by allowing them to have different base pays. All right, regarding the interpretation, again, I want to go back to if you look at the combined model and erase the U sub 0j, this is exactly the same as our old traditional simple regression. And if this were the simple regression, if that U sub 0j weren't there, then gamma 0 would be the same thing as beta 0. That is the base pay when skill is 0. And that's exactly what gamma 0 means within this context. Similarly, in the combined equation, if we were ignoring the U sub 0j, gamma sub 1 0 would be the old beta sub 1, the coefficient of x, and that would represent the change in salary when skill increases by 1. And that is exactly what gamma sub 1 0 means now. The only distinction is that gamma sub 0 and gamma sub 1 0 are now interpreted that way with the addition to their interpretation of the fact that these are interpreted that way after accounting for the differences in company base pay. So this is accounting for the U sub 0j, but the main interpretation for both of these components is identical to their simple linear regression forms. The U sub 0j again represents the intercepts or the base pay that is adjusted for each company. This is a random effect. I don't know what this is going to be, and it's allowed to vary. But ultimately, what this lets each company have is a different base pay. Again, our interpretations are after accounting for the company differences in base pay. So we are accounting for this nesting through letting that intercept be different. And otherwise, gamma sub 0 is exactly the same interpretation of our old beta 0, and gamma sub 1 is exactly our old interpretation of beta 1. We just add that bottom bullet point component to those interpretations. So go back, revisit your old simple linear regression interpretations, and these are exactly the same thing. And again, this is why I like this random intercepts model so much, is because all of my coefficients maintain that interpretation from my regression. So if I worked on my regression interpretation, I get to keep all of those skills and all those interpretations that I had. I just add that bottom bullet point component of after accounting for the level 2 differences in the intercept, or in our particular case, after accounting for company differences within base pay. All right, so let's look at our data, and let's actually look first at a normal regression. That is, I'm going to look at the relationship between skill and the salary without worrying about any of these details of accounting for company or anything. I just ignored all the nesting. And this is what I would get is that line. Now, when I allow for nesting specifically with the random intercepts, again, I'm going to get a different line for every company. But all of the slopes are the same all that's allowed to change per company is the intercept. And under those conditions, this is what that model looks like. The dotted line represents the fixed components of our model, and you'll note that all of these different colored lines are parallel. That is, they all have the exact same slope, but they're at slightly different heights. That is us letting the intercept be different for each one of these models. And this is a graphical representation of the random intercepts model. All right, let's talk about the random intercepts and slopes model. And this is going to pretty much keep all of our components. Now, we're not really looking at the level 2 independent variables, but otherwise, it's going to let our intercepts vary by company and let our slopes vary by company. The combined form, multiplying this out, I can see the first two components, gamma sub 0, 0 and gamma sub 1, 0, are the fixed effects components. That is kind of the average across all of the companies for the intercept and the slope or skill compensation. And then I let the company adjustments happen. That's the U sub 0j, that's the company adjustments to the base salary, and the U sub 1j, that's the company adjustments for the skill compensation, or uh, again, the company adjustments for every increase in skill, how much salary changes. I prefer skill compensation. So the company adjustments for the skill compensation. So this model is used to test exactly the same thing we looked at before, the relationship between skill and salary. But this I would use if I believed that skill compensation changed based on company, which may be a good assumption or may be a good thing to believe in this particular case. The interpretations of gamma sub 0, 0, gamma sub 1, 0, and U sub 0j are all exactly the same as before, so I'm not going to revisit them here. The only additional component is that instead of just after accounting for the company differences in base pay, now these will be interpreted after accounting for company differences in base pay and skill compensation. The U sub 1j, again, is the skill compensation adjustment per company. So it's where I let those companies differ based on the skill compensation within each company. And again, the interpretation is just adding on this additional component after accounting for company differences, not just in base pay, but also in skill compensation. When we add on the random slopes model, it's important to realize that this is a form of interaction. That is, what we're saying is that the relationship between the skill and salary may depend upon the company the individual is in. And that whole may depend or depends on is an interaction between the variables of company, the level 2 general variable, and skill, the level 1 independent variable. So we do want to be careful here that any interpretation of gamma sub 1, 0, the average relationship between skill and salary, may or may not be a good general interpretation, depending on how much companies vary in this. So if companies vary very widely in this, some companies don't provide any additional compensation for skill, and some companies provide massive additional compensation as your skill increases. It may not be appropriate to interpret the average among all those. It might be better to say, hey, it depends on which company you're in. Some companies, it's the gamma sub 1, 0 is really non-existent. For some companies, it's a massive number. So again, this is a form of interaction. We do want to be a little bit careful about that. And we do want to probably interpret the U sub 1j, that interaction term between the groups and the skills impact on salary before we look at the overall main effect of skills impact on salary. Let's check out what this looks like in a graphic. Here's our main data, and let's look at the random intercepts model that we had before. So I had my fixed effects, that's the average over everybody, that's the black dotted line. And then I let each of the companies have their own intercept. So they all shared the same slope, they all have that same diagonal line, but they can move up and down. That is, they have different intercepts. Now, with random intercepts and slopes, not only are they allowed to differ where they meet the y-axis on the left-hand side, but they're allowed to differ in their slopes. So this graph becomes a lot messier because each company may have a different slope or a different skill compensation that they provide. And this is a graphical representation of our random intercepts and slopes model. All right. Well, those were some big three models. Let's talk about a couple of other things. And these are kind of ancillary. They didn't really fit anywhere else, but we should talk about them. First, if we centered skill, and we talked about centering beforehand, especially in the context of the interaction, the base pay, as we interpreted it, that beta zero, now becomes average pay because when skill is zero, it's no longer the salary when you have zero skill. If we centered skill, when the centered skill is zero, that becomes the salary when you have average skill. So that would become our average pay instead. Now, in the examples I just showed, we didn't include any company level variables, but we absolutely can interpret company level variables. And we can interpret these normally when we include them. It's the big benefit of including company level variables in the hierarchical approach is the fact that we're using the correct standard errors for these. So again, we're avoiding some of those type 1 and type 2 error problems. Specifically, type 1 errors, what we get concerned about. Well, actually, a little bit of both, but specifically type 1 errors, what we get concerned about with the level 2 independent variables. We can look at the interactions between level 1 and level 2 variables as well. And again, we can interpret these normally too, because the model is accounting for the fact that I have cross-level interactions going on, and some of the statistical backend is taking care of this, which is really, really handy. For the random components, it's important to realize that these are a little bit different. I feel like sometimes students expect, and I know that when I first learned this, I expected that just like typically we're going to get a number, in our old regression, beta zero had a number associated with it, beta one had a number associated with it. In our new model, the gammas are going to have numbers associated with them, but the u's are not. So the random components allow the level one things to change per company, but that means that we're going to have a company by company adjustment when we include the U's, that is the random components in level two. Because it's a company by company adjustment, there isn't really a single number that works. Each company is going to have their own adjustment that they can use. There's going to be one per company or one per level two group. And we just account for these. We don't really interpret these necessarily. We can, again, look at the variability. We discussed this earlier in things like the interclass correlation coefficient, where we look at the variability in these and determine how much variability in these adjustments is related to the total variability of the data. And if we have more variability that's related to the level two variable, then we would believe that the level two variable is more important. All right, so how do we analyze the data? Like, what do we do now that we've kind of learned all this? And the process goes like this. If you're studying data with nesting, hopefully now you're going to have a big flag in your mind that says, hey, I'm using nested data. I need to remember to go back to this hierarchical linear modeling thing. And hopefully this analysis pops into your head. What you're going to do is hierarchical linear modeling is just a regression, just like normal regression. So you still have to check all of the regression assumptions. And then you'll check your intraclass correlation coefficient to determine if your level two has an effect that you need to account for. So I might look at normality. Some of the regression coefficients or the regression assumptions I can't test until after the models fit, so I'll leave those for later. But in the overall process, even once my models fit, that's going to be the thing that I look at before my interpretations. In any case, I'll check those assumptions to the best of my ability. I'll work on the interclass correlation coefficient to see, does level 2 contribute anything? And if it does, if it includes a meaningful amount, I can check the statistical significance. I can check the practical statistic significance with the interclass correlation. And if it does contribute a lot, then I'm going to include it for sure. And if it doesn't contribute anything, then maybe I choose to not include that nesting structure and just go about with my analysis normally. Now, I will say if there's a theoretical reason why you expect nesting or why you had nesting, even if you check the interclass correlation and it doesn't seem like a particularly large nesting effect, you probably should account for it anyway. So if there's a reason that you think that the data are nested, if you collected data on individuals within department, on employees within department, or employees within company, you collected data on students within classroom, you really should probably be accounting for nesting even if it doesn't show up in the ICC statistic. I should also add, if the intraclass correlation is pretty small, interpret those level 2 variables pretty modestly. Think about this as if only 1% of the variance in salary is explained by company, then whether the company is public or private, that's only going to impact that 1% of the salary that was explained by company in the first place. So that interpretation should be made relatively modestly, even if it's statistically significant. That should be good to know, but interpret it in light of the total variability um, explained by level 2. So after we've checked the ICC, we can look at how the level 2 company impacts the level 1. And what we do then, after we've determined that level 2 is an important thing to account for, is we want to look at what our hypothesis and question relate to. So for instance, if I hypothesize that companies have different base pays, that's going to tell me to use a random intercepts model. If I hypothesize that companies have different skill compensations or value monetarily skilled differently, then that's going to tell me to use random slopes. And if I hypothesize both of those, then that's going to tell me to use both of those, random intercepts and random slopes. I will say the random slopes alone is never really used. So if you're doing a random slopes model, you'll also drop in the random intercepts model to help with that. Yeah, random slopes is never really used even once variables are centered. So yeah, we would use the random intercepts and the random intercepts and slopes depending on the question and what we believe about the data, what we believe about the situation. In our case, how we believe companies relate to employees' skills relationship with salary. All right, well, this has been some details on model building and the analysis process. We'll close out our HLM video lecture set lecture slides with a full example of this process, including the interpretation.